Now let's focus on what we talked about in the last video when we were talking about stress. Let's focus on the normal direction or the axial direction where we define stress. So now if we were looking at those things working in the z direction, what we had said is that the limit as delta A approaches 0 of that force, so the infinitesimal forces in the z direction over the infinitesimal area, we were defining that as sigma z, or the normal stress in the z direction. So in more general terms, what we'll end up saying is we'll say that sigma z, or x or y, it doesn't really matter, it's all the same, is going to be pz, which is the internal load in the z direction. So load in z direction divided by the cross-sectional area over which it's acting. So, area. The important word here is internal load. So we need those internal forces. And so when calculating stress, much like calculating loads and stresses, the sign tells us what kind of stress that we're looking at. So remember that positive is a tensile stress. That negative is a compressive stress. And once again, this is important because different materials will have different properties in those directions. So, as I had said before, forces don't matter in the system because it doesn't really matter. I have a 1,000,000-pound force in this member. Is it going to break? Well, that doesn't tell us anything because 1,000,000 pounds is just an external force. Now, if that 1,000,000 pounds is applied over 1 square inch of space, well, that's going to be 1,000,000 pounds per square inch, load over area. And so that probably is going to tell us something, but then, once again, it's going to depend on the material. Now, that is an important thing to bring up, is we're going to be talking about the units. And units are critically important. We're engineers. Units matter a lot. And so as we break this down, as we look at it, we're going to do just a unit analysis here of our force over area is equal to the stress. Well, our force is just going to be that. It's going to be in units of force. We're going to divide that by area. Area is given to us in units of length squared. If you've never seen this notation before, this is, especially in fluids, is a way that we can look at what the units are going to be. And so that tells us that stress is going to be in units of force over length squared. So what does that mean? Well, that means in the metric system, our force would be a Newton, and our area is going to be the length, which is going to be a meter squared. Now that is really small. So if you think about it, and let's just think about a square meter. So a square meter is 9 square feet. So if you've got tiles in your house, the tiles are probably 1 foot by 1 foot. So go and look at how big 9 of those tiles together would be. Now, a Newton is a unit of force. Now, I know we're not really big on the metric system, so we don't have that innate comprehension of what a Newton is. Now, way back when I was in school, my physics professor told us this dumb story, which is why I remember it. Dumb stories are the best because they stick in your head. When I was growing up, McDonald's had introduced the quarter-pounder hamburger. So that was a new thing when I was a kid, just to show you how old I am. My physics professor had said that McDonald's missed out on a key opportunity to help teach the United States the metric system because they should have called that a Newton burger, because a Newton is roughly a quarter of a pound of force. So now, with that image in mind, think about how much force that quarter-pounder hamburger, which is only the patty, is when you spread it out amongst those 9 tiles in your bathroom. Newton per meter squared is a pathetically small unit. So what happens? Well, one, Newton per meter squared does have an alternate definition in the metric system. They call that the Pascal. which is typically shown as PA, and that is a Pascal, named after the scientist. And so typically what you will see in a material properties book in the metric system will be MPa and GPa. So this is megapascals and gigapascals. And so a megapascal would be times 10, scientific notation, 10 raised to the 6th power pascals. Gigapascal is 10 to the 9th pascals. So you will see typically mega and gigapascals as the unit for the metric system. Now we look at the English system, specifically the British gravitational system, which is the normal one that we're used to. And we're going to be looking at the unit of force will be the pound force, and we'll divide that by the base unit would be the inches squared. Now typically you will see this written as PSI. PSI is just pounds per square inch. Now the one that you will see a lot in the English system would be what's called the KSI. And what is the KSI? All a KSI is 1,000 PSI. So anytime you see a KSI, that's just 1,000 pounds per square inch. Now typically this is what you'll see material properties in books will be listed in KSI. And so that is our basis of normal stress and the units behind it. And so in the next video, we're going to apply that to a problem.